Hello everyone. I am Udaya, working as Assistant Professor in the Department of Agricultural Engineering, Sri Shanmuga College of Engineering and Technology. In this lecture video, we are going to discuss about the topic interaction of EMR with atmosphere. That is interaction of electromagnetic radiation with atmospheric features. Okay, so electromagnetic radiation starting from sun. So on its way to the Earth's surface, it travels through the atmosphere. In atmosphere, what are all the changes or phenomenon occurring to that radiation? So that this is what that we are going to discuss in this topic. As you can see in this image, so it contains a lot of process like absorption, scattering, and transmission, emission. So there are these kind of phenomenon that is happening to that incoming radiation in the atmosphere. Okay, we are going to discuss these features in detail. So let us start. So the radiation from the energy source passes through some distance in the atmosphere before being detected by the remote sensor. So the incident radiation from the sun travels through the atmosphere two times. Okay, one on its way to the Earth's surface, the next time as a reflected radiation. So in both the times of travel, it undergoes so many changes. Okay, so that is scattering, reflection, refraction, emission. We can discuss now. The distance traveled by the radiation through the atmosphere is called the path length. The path length varies depending on the remote sensing techniques and sources. So, for example, the path length is twice the thickness of the Earth's atmosphere. As I said, it travels twice. For airborne thermal sensors, which use emitted energy from the objects on the Earth, the path length is only the length of one-way distance from the Earth's surface, and it's considerably small. Uh, the effect of atmosphere on the radiation depends on the properties of the radiation, such as magnitude and wavelength, the other atmospheric conditions, and also the path length. The interaction of EMR with atmospheric particles may be a surface phenomenon, that is scattering, or volume phenomenon, that is absorption and refraction. Okay, scattering and absorption are the main process that alter the properties of electromagnetic radiation in the atmosphere. Now let us see what is atmospheric scattering. Okay, so atmospheric scattering is in general, it is the process in which the small particles in the atmosphere diffuse a portion of the incident radiation in all directions, and there is no energy transformation that happens while scattering. But the spatial distribution of the energy is altered during scattering. There are three different types of scattering. One is Rayleigh scattering, Mie scattering, and non-selective scattering. Non Rayleigh scattering. In Rayleigh scattering, the first thing is that the particle which is responsible for the process scattering is much smaller than the incident radiation. Okay, the particle size is very much smaller than the size of incident radiation. So smaller particles present in the atmosphere scatter the shorter wavelengths compared to the longer wavelengths. So the size is almost less than one tenth. The size of the particle is very small. It is almost one tenth of the size of the incident radiation. Okay. The mainly the sky appears blue because of this Rayleigh scattering. Okay, the scattering effect or intensity of scattered light is inversely proportional to the fourth power of wavelength for Rayleigh scattering. Here the shorter wavelengths are scattered more than longer wavelengths. Rayleigh scattering is also known as selective scattering or molecular. The second type of scattering is Mie scattering. In this scattering, the size of the particle causing scattering is almost equal to the diameter of the incident radiation. Okay, here the particle size and the incident radiation both are same. Okay, so Mie scattering, you can see in the image Rayleigh scattering, Mie scattering, and non-selective scattering. In Rayleigh scattering, the particle size is very much small. Mie scattering, the particle size and the incident radiation both sizes are equal. The third one is non-selective scattering. Before that, we will discuss the examples of Mie scattering. The particles such as dust, smoke, and pollens, some gas molecules in the atmosphere are responsible for Mie scattering. Then coming to the non-selective scattering, non-selective scattering, the particle size is much bigger than the incident radiation, almost 10 times bigger than the incident radiation. Particles such as pollens, cloud droplets, ice crystals, raindrops, they are all responsible for non-selective scattering. So for visible light, zero point 0.4 to zero point 0.7 micrometer, non-selective scattering is generally caused by water droplets, which is having a diameter commonly in the range of 5 to 100 micrometer. This scattering is responsible for white or somewhat mild gray color of the cloud. So the scattering is non-selective with respect to wavelengths, since all the visible and infrared wavelengths get scattered equally. The next thing we can discuss is atmospheric absorption. The most efficient absorbers of solar radiation are water vapor, carbon dioxide, and ozone. They absorb all the incoming radiations by some of the gases which are present in the atmosphere. Gaseous components are the selective absorbers of the EMR. That is, these gases absorb electromagnetic radiation in specific wavelength bands. The next thing about EMR interaction with the atmosphere is that atmospheric windows. The atmosphere contains many different gases and particles that we all know. It absorbs and transmits many different wavelengths of electromagnetic radiation, even though all the wavelengths from the sun reach the top of the atmosphere due to atmospheric absorption. Only limited wavelengths can pass through the atmosphere. Okay, so the range of wavelengths that are partially or wholly transmitted through the atmosphere. So that pathway is called atmospheric windows. Okay, remote sensing data acquisition is limited through these atmospheric windows. As you can see in this image, the path, these paths like UV, visible, infrared, and some of the regions in the infrared, near infrared, mid infrared, and thermal infrared, the one having longer wavelengths, that is microwave region. These are the passages which allows the electromagnetic radiation to pass through it. The other gray shaded portions blocks the energy. Okay, so this phenomenon is called atmospheric windows. The next topic about EMR interactions in the atmosphere is refraction. Okay, so the phenomenon of refraction that is very common in our physics, that is bending of light at the contact between two medium, also occurs in the atmosphere as the light passes through the atmospheric layers of varied clarity, humidity, and temperature. So these variations influence the density of atmospheric layers, which in turn causes the bending of light rays as they pass from one layer to another layer. The most common phenomenon or the most common example of refraction is a mirage-like appearance. When we travel in the summer days, we will be able to see the presence of water at a long distance, but actually the water will not be there. Okay, so this mirage, we call it as mirage. So this phenomenon occurs due to atmospheric refraction. Okay, so I hope this video will be would be useful to you in understanding the interactions of radiation with the atmospheric features. Thank you. Thank you for watching.